So yesterday's lesson, we learned how to find the limiting reactant. And today we're going to talk about how to use the limiting reactant to determine how much of a product would form. So in the example from the notes yesterday, we did 2A. And we determined that the least amount that was produced was the 0.250 moles of nitrogen. So that meant that the H2O2 was the limiting reactant. So for part B, it says how many moles of water are formed. So since water is a product, we're going to have to use the limiting reactant to figure out how much will form. So you always start with the limiting reactant in order to figure out how much of either product will form. Now, I would go back into the original part A problem. I would not use the answers from here because you might have made a mistake and you don't want to use a incorrect number to start part B. So since the limiting reactant is the H2O2, I'm going to use 0.500 moles of H2O2 as my given. And in the problem, it wants us to figure out how many moles of water are formed. So I'm going to put here moles of water. So mole of H2O2 to mole of water is a one-step conversion. We need our mole ratio. So on bottom, get your units to cancel. You need moles of H2O2. And on top, you need to put moles of water because that's what you're trying to calculate. The mole ratio numbers come from the balanced equation. So for the water, we see a 4 coefficient. So we put a 4. And the H2O2, we have a 2. So 4 to 2 ratio. So this lets moles of H2O2 cancel. And so 0.5 times 4 divided by 2 is going to give us 1.00 moles of H2O for our answer. We have 3 sig figs here. Remember that the coefficients are counting numbers, so they have unlimited sig figs. So our answer should have 3 sig figs. All right, let's look at part B of number 3 that we looked at yesterday. So this wants to know what mass of zinc sulfide can be produced. So again, we're going to start with our limiting reactant. We said that was zinc. So in the beginning of the problem, we were told we had 2 moles of zinc. So that's what you're going to start with, 2.00 moles of zinc. That's your limiting reactant. And in this example, we're trying to go to mass of zinc sulfide. So grams is our unit for mass of ZnS. Moles of A to grams of B is a 2-step conversion. So first thing we need is to get moles of zinc to cancel. And this is our mole bridge. So we're going to put moles on top of who we're trying to convert to, which in this case is zinc sulfide, so ZnS. Now from the balanced equation, there's an 8 and an 8 in front of both of those. So it's a 8 to 8 mole ratio. This lets moles of zinc cancel. Now we need moles of zinc sulfide on bottom and grams of zinc sulfide on top. This is our molar mass. So molar mass is always grams per 1 mole of zinc sulfide. If you add up the molar mass of the zinc sulfide, you will get 97.46 grams per mole. When you plug this into your calculator, you end up with 195 grams of zinc sulfide that will form. All right, so let's look at the final concept for this chapter 12 on stoichiometry, which is called percent yield. Percent yield is something that we can calculate to determine the efficiency of our reaction. The formula that we use for percent yield, you see here in the oval, it's percent yield is equal to grams actual divided by grams theory times 100. Now, grams actual represents the amount that you actually formed or obtained in the lab or in the experiment. Grams theoretical, this represents the maximum amount of product possible to form. So if you were to get 100% yield, which is impossible to do, but if you were to get 100% yield, the grams theory represents how much is the most you could make. Now, we have to always calculate grams theoretical. That's the always thing. You got to calculate it. And it's just like what we just did in the limiting reactant problems for part B, those part Bs, where we start with the limiting reactant and we then convert it to grams of the theoretical substance. This will be a three-step conversion, a gram of A to grams of B problem. So let's look at an example from our notes. Here we have an equation, and if you check it, always check it to see if it's balanced, and this one is already balanced. It's a 1 to 1 to 1 to 1 mole ratio. So of course they tell us some information. Chlorobenzene is used in the production of chemicals such as aspirin, dyes, and disinfectants. It's prepared by the above reaction, yada, yada, yada. Here's where we get the important information for the problem. 36.8 grams of C6H6 reacts with excess chlorine. The actual yield of the C6H5Cl is 38.8 grams. Calculate the percent yield of C6H5Cl. You must always calculate Graham's theory, and you want to start with the limiting reactant. Now, they didn't come right out and tell us the limiting reactant here, but they did in a way. They told us it's reacting with excess chlorine. There's only two reactants up here, class. If the chlorine is your excess, then that means that the C6H6 is your limiting reactant. And they did tell us how much of him we had. So start with the 36.8 grams of C6H6. Now, since we want to find percent yield of the C6H5Cl, that's who we need to find Graham's theory of, C6H5Cl. This is going to be a three-step problem always. All right, let's get our units in place. And I'm going to, just for time's sake, go ahead and tell you what the molar mass is. If you want to pause the video, if you want to try it on your own, go ahead and pause the video now. Okay, and now we need moles of C6H6 on bottom. This is where our mole bridge goes in our three-step problem. And it was a 1 to 1 mole ratio. Here, grams. And that's of the C6H5Cl. Molar mass of the C6H5Cl is 112.56. Now, this is going to allow us to calculate grams theoretical of the chlorobenzene. I'm sorry, yes, of chlorobenzene. So this is going to give us 53. Plug it in your calculator. Make sure you get this. Verify you get the same thing. 53.0 grams, and that's just 3 sig figs. So this is our grams theory. So now we're going to use that and plug it into our formula. Percent yield was grams actual divided by grams theory times 100. They told us the actual yield up here, 38.8 grams. So that plugs in for grams actual. Grams theoretical, you just found. This is going to plug into the denominator, 53.0, and then multiply by 100. So when you do that, you get your percent yield. This is a percent yield of 73.2%. The final example here is this equation is also needs to be balanced. So it's a 1, 2, 1 to balance that equation. This says you have 75 grams of carbon monoxide reacting with excess hydrogen. So again, hydrogen is the excess. It does help to label this up here. Carbon monoxide, therefore, is your limiting reactant. And it says to produce 68.4 grams of CH3OH, what's the percent yield again? So let's find grams theory first. Remember to start with your limiting reactant. Which is 75 grams of CO. And we're going to convert that to grams theory, which is the CH3OH. That's the compound we know the grams actual for. So we need grams of CO on bottom. This is our molar mass of carbon monoxide. And the molar mass of that is 28.01. We need the mole bridge next. Moles of CO here. Moles of CH3OH here. And that's a 1 to 1 if you look at the balanced equation up here. Molar mass of CH3OH is 32.05. That's going to give us a theoretical. The maximum we could make is 86 grams